So I'm a research astrophysicist at a museum in the department founded by someone some of you may have heard of, Neil deGrasse Tyson. And what I want to talk to you about today is the very interesting situation that we found ourselves in learning about the universe. Because we are living in a time where we have understood that the universe is far stranger than we would have thought. If we go back to medieval times in Europe, the Earth was thought not as being at the center of things, but at the bottom of things. It was where all the dreck and garbage and sin fell. The heavens were pure. The heavens were where God lived. The earth, not so much. During the Enlightenment, Copernicus and his peers said, well, wait a moment, things aren't so bad. Maybe the earth isn't actually all the way at the bottom. Maybe it's somewhere in the middle. And the sun is at the bottom. This was the principle of mediocrity, which was far better than being at the very bottom of the scale. Well, this was an interesting idea, but when it was implemented mathematically, it was found that if you still assumed that the heavens were pure and that heavenly bodies moved in perfect circles, you hadn't actually progressed very much from Ptolemy's ideas that you had circles and then epicyclic smaller circles that explain planetary motions. Now, it turns out that Ptolemy's ideas lasted for so long, partly because the system he set up was very, very good. It could explain the motions of the planets and make predictions that were extremely accurate. He did this by making some special purpose adjustments, not just the epicycles, but every planet did not go around the Earth. It went around the equant, which was a point off the Earth that you had to assume to get the planets to behave properly. So there were a lot of special purpose fixes, but it was a system that worked. When Kepler, the guy up there, drops the assumption of circular motion and assumes ellipses, yes, it's a much simpler system, but the difference in predictive power was a matter of 8 seconds of arc in position of the planet Mars. 8 seconds of arc is the width of a coin 10 blocks away. You needed huge naked eye instruments to even measure that. You had to sight along that extremely long arm and swing it back and forth to measure the angle at which you were observing something. So already in the naked eye era, we're talking large instruments and great observational dedication to understand the fundamentals of our universe. During the same period, the first telescopes start to be built. Galileo didn't invent the telescope, but he was an early adopter, and he was aggressive in getting the word out that, wait, the heavens are not pure. There are mountains, there are craters, there are imperfections on the moon. This picture, by the way, was taken by Galileo, the spacecraft, on its way to Jupiter. Well, now we had some understanding of the solar system, that it was a heliocentric solar system with planets moving in imperfect ellipses. To step out further, we had to understand the distances to the stars. And this took hundreds of years because the stars are very far away. You can measure their distances with parallax, but parallax, right? You hold out your finger, and if it's close to you and you go one eye to the other, you'll see it move a lot. If you move it out further, it doesn't move as much. Well, stars move fractions of a single arc second. So you needed substantial telescopes in order to make that measurement and understand that the stars were trillions of miles away. Parallax only gets you so far if you don't have a telescope in space that's outside the Earth's atmosphere. And the next step was one of the first instances of the application of what we now call big data. Now, at the turn of the last century, around 1900, a computer was not a machine, it was a profession. These were computers at the Harvard College Observatory. They were the people who were in touch with the data, who were actually working with it, and they made some very important discoveries. One of them, Henrietta Leavitt in the center here, was the person who realized that the variability period of a certain kind of star called a Cepheid correlated directly with its brightness, as shown in that graph up there. The brightness going up, the period going to the right. So if you could watch something varying, you knew how bright it actually was. By measuring how dim it appeared, you could see its distance. That allowed us to measure the distance across our own galaxy, and even more importantly, to other galaxies, and to understand that other galaxies were objects like our own Milky Way galaxy, but outside of our own. Now, if the universe is a static and unchanging universe as we perceive it on the human scale, then those other galaxies like our own ought to move like this. Here we are at the center of the image. The galaxies that are moving towards us, their light gets squeezed a little and moved to the blue. The galaxies that are moving away from us, the light gets stretched and moved to the red. It's called blue shift or red shift. It's the principle on which the radar gun works. If the cop points the radar gun at your car and the returning waves are shifted too far to the blue, you get a ticket. Galaxies should have been moving randomly. When measurements were taken of distant galaxies, this was not the result. This was. So the guy up here, Vestos Slipher, finds that practically every galaxy is moving away from us, is redshifted. Only a few nearby galaxies are moving towards us. Okay, I'm going to show you a clip from a space show that we did at the museum called Dark Universe. And this is our galaxy. As we pull out, we will see an accurate map of all the three-dimensional positions of galaxies that we have measured and their velocities. There's the Andromeda galaxy. Hubble was the first person to find a Cepheid variable in the Andromeda galaxy and show that this was not just a fuzzy nebula like the nebulae in our own galaxies around star-forming regions, but was a different object. And here we are in the universe of galaxies. They have structure, and that structure we'll talk about later. But these galaxies are all expanding away. Now, if all the galaxies are expanding away from you, there are two possibilities. Either you are a very lucky person and you are sitting right at the center of the universe, which some people believe, or it's not just us. Everybody sees expansion. So this galaxy sees expansion, but so does another galaxy. And if that is true, then the entire universe must be expanding. It's not just expanding out into something. Everywhere is expanding. Every point in the universe is expanding away from every other point. Objects that are bound together by chemical forces or gravitational forces, space expands out from under them. That's why we're not expanding, happily. But if every object is expanding from every other object, then if you project backwards in time, things must have been once much, much denser, and therefore much, much hotter. And that is the fundamental reason for believing in the idea of a Big Bang. That once the universe was extraordinarily hot and dense. In fact, once the universe was as hot and dense as the surface of the sun. And the light emitted at that time, which was visible light at the time, has been traveling through the universe and getting stretched out as it travels, so that it is now shifted from the visible light to the infrared light to the microwave. And this is the cosmic microwave background. The very small variations in which were measured in this map by the Planck satellite and have been measured over the years. Okay, so we have a universe that's expanding from an origin. When this was first proposed, it was denounced as creationist, and indeed it was proposed by a Catholic priest, Father Lemaitre. And yet, all the evidence that we have points to the idea that the universe started at a definite time, extraordinarily hot, extraordinarily dense. Furthermore, most of the matter in the universe is not the stuff we are made of. It's not atoms of any sort. The first person who realized this was this guy up here, Fritz Zwicky, back in the 1930s. He looked at galaxy clusters and realized that there was far too much mass in them. They couldn't be explained by the visible galaxies. He measured how fast galaxies were orbiting using their redshifts and compared it to how much mass was in the stars whose brightness he could measure. And the answer came out, it was 100 times wrong. There was 100 times more mass in that cluster than could be accounted for by the visible galaxies. Well, back then, first of all, he was a famously foul-mouthed and paranoid guy who nobody liked. And second, we didn't really understand galaxy clusters, so everybody just sort of shoved it to the side. Until the 1970s, when Vera Rubin comes along and looks at individual galaxies and how stars orbit around the center in those galaxies. And she finds that if the stars were in the galaxy, if the stars were the only mass in the galaxy, they should orbit like this line labeled disk. And yet they don't. They orbit like the top line, meaning there's lots of extra mass. After that point, people started taking the idea of dark matter seriously. Given the timing, we're going to keep going, because that was bad enough. But still, we understood that now we know where all the mass is. And mass will act on the expansion of the universe to slow it down, because gravity is pulling it in. Now, to measure the mass well, it would be good to know how quickly the universe is decelerating, how quickly that expansion is slowing down because of all the mass in the universe. And so a number of teams in the 1990s set out to measure the deceleration of the universe by measuring galaxies at great distances and finding their redshifts. They used a certain type of supernova that could be calibrated to reveal its absolute luminosity, how bright it actually was, and compare it to its apparent luminosity. And they went out and found lots of supernovae with great effort and built robotic telescopes to do this. And at the end, it came down to this guy over on the left, who is a graduate student in the group, taking all the data, putting it together to measure the deceleration of the universe. And so late one night, he finishes the program and adds up all the numbers and gets out the answer, and he's got a sign error. The deceleration is negative. It's not a deceleration at all. It's an acceleration. Well, he goes back and gets his boss and his boss's boss, and they all check the numbers, and it remains an acceleration. It turns out that there's something else besides matter, and it is dominating the dynamics of our universe. We've given it a label. We've called it dark energy. It's energy that we cannot detect, so it's dark. We know that to about 10%, it hasn't changed over time. There's not more and more of it. But yet it is causing our universe to go faster and faster. So we are starting to characterize it more and more accurately, but we still don't know physically why it's there, why it is as strong as it is. Now we have now accomplished multiple independent measurements of how much dark matter there is and how much matter there is. And this is the cosmic microwave background. This is the supernovae. The other one is measuring the positions of galaxies and how fast they're falling together. They come together in that very small error circle. And that small error circle is a place that is extraordinarily odd. It is a universe dominated by dark energy and dark matter. Everything that we know about and can detect at this point is in that little 4% sliver, of which only this little red sliver over here is the heavy elements, the carbon, the nitrogen, the oxygen, all the stuff that makes up us, our planets, aside from hydrogen. Most of the universe has not yet been detected. Dark matter is perhaps on the cusp of being detected. There are many efforts being made to directly detect a dark matter particle. They may be successful, possibly soon. Dark energy, we're still in the mode of, I'm a blind person and I'm feeling the elephant. Is it have a long, skinny bit? Is it a big, hard bit? What is it? That's how we're living in the question of understanding our own universe. Thank you.